So in this video we will be going to discuss about the linear fractional transformation, how they can be constructed with the help of only 3 points on the domain plane and their corresponding images on the W plane, right? In the last video we saw that how a linear fractional transformation can map circles to circles or circles to lines, right? And in this video we will see that the linear fractional transformation can be constructed with the help of a cross ratio, right? So first I will define what is a cross ratio. Cross ratio if you have if z1 or I say z1, z2, z3 and z4 are 4 points, then the ratio are given by z1 minus z2, z2 minus z3, z3 minus z4 over z4 minus z1 is called cross ratio. Okay, so this is called cross ratio. You need just 4 points in order to write this ratio, and with the help of this cross ratio we can identify or we can find a linear fractional transformation, right? You need exactly 3 points of z plane and 3 points of the image plane, W plane, and on applying this cross ratio property you can find the linear fractional transformation, right? But the fact is that under this linear fractional transformation the cross ratio is always preserved, right? It means that the cross ratio within the 3 numbers of z plane is equal to the cross ratio of 3 numbers corresponding 3 images of the W plane, right? So under this transformation, linear fractional transformation, and we denote it by Wz equal to Az plus B over Cz plus D, where AD minus BC is not equal to 0, right? So this is called linear fractional transformation. The cross ratio is preserved. The cross ratio is preserved, right? That is for any 3 points z1, z2, z3, and if I add the 4th point as z, so z, z1, z2, z3, then the cross ratio will become z minus z1, right? And z1 minus z2, then z2 minus z3, and z3 minus z, right? Because we need W in terms of z, so I am setting the 4th point as z, right? You need not to take all the 4 points as complex number. One of them should be z, because we need W in terms of z, right? Otherwise I will get a number here, right? So that's why I have used z, z1, z2 and z3, and similarly here W minus W1, W1 minus W2, W2 minus W3 and W3 minus W, right? So this is called the preservance of cross ratios, right? This is the cross ratio for z plane, this is the cross ratio for W plane, and since the cross ratio is preserved they must be equal, and we can, using this formula or relationship, we can find the W in terms of z, right? Okay, so this will be used in examples, right? So I will start with example number 1. Find the bilinear transformation. As you know that the bilinear word is also used in place of linear fractional transformation. And why we use this word bilinear? Actually, if you cross multiply this, you will get an equation in W and Z, right? And if you consider that equation in variable W, you will see that only first power of W is occurring in that equation. It means that this equation is linear in W, as well as this equation will be linear in Z if you cross multiply it, right? That's why this bilinear term is used. Bilinear means linear in 2 variables, one in W and one in Z separately, right? And the bilinear transformation which maps the points, and if I take the points on circle, this is 1, iota and -1 on unit circle mod z equal to 1 onto the points -1, 0, 1 on real axis, right? And also find the image of interior of circle. It's called interior, the inside of unit circle, right? The solution, I will use this cross ratio technique, and to use this formula I just need 3 points on z plane, z1, z2, z3, and 3 points on w plane, w1, w2, w3. And do not forget that you should not change the order of these points, right? This is z1, z2, z3, w1, w2, w3, right? So let z1 equal to 1, z2 equal to iota, and z3 equal to -1, and from here w1 equal to -1, w2 equal to 0, and w3 equal to 1, right? Now I will use this formula, and that will give me, using cross ratio, I will have z minus z1, z1 minus z2, and z2 minus z3, and z3 minus z, and similarly w minus w1, that will be +1, w1 minus w2, and w2 minus w3, and w3 minus w, right? So this is the relationship we obtained after applying that cross ratio, and now I will simplify this. Maybe I will be applying componendo or dividendo, right, in order to obtain w in terms of z, right? So that will produce, I think I have to simplify it, or z minus 1, and if I rationalize this, I think it should be 1 plus iota. If I rationalize it with 1 plus iota, then in the numerator I will be getting 2, denominator 2, and since 1 plus iota is multiplied with this, that will produce 1 plus iota whole square, and that will produce 2 iota, right? So be careful at this point, you have to rationalize it, and this will produce minus common z plus 1, right? And similarly here w plus 1, and this minus 1 and minus 1 will be cancelled out, we will be left with minus times of w minus 1. So ultimately this minus and minus will be cancelled, right? Or I will be having z minus 1, and iota is also here, right? So iota over z plus 1, 2 and 2 is cancelled, minus minus is also cancelled, equal to w plus 1 over w minus 1, right? Now I will apply componendo and dividendo in order to obtain w in terms of z. Apply componendo and dividendo, right? Or you can just cross multiply them and then express w in terms of z. That is also possible. So on applying componendo and dividendo, I will get here iota z minus iota plus z plus 1, and iota z minus 1 minus z minus 1, and here I will have this plus this, numerator plus denominator will produce 2w, and this minus this will produce 2, right? And 2 and 2 will be cancelled out, that will produce w equal to this thing, I think iota 1 plus iota z plus 1 minus iota over, and the denominator I will be having z iota minus 1 and minus 2, right? So this should be the transformation, right? And let me check whether it is correct. If I plug 1, I should get -1. So if I put 1 here, that will be 2, and it will become eta minus 3. I don't think it is correct. On putting 1 we should get -1, and on putting eta we should get 0. If I put eta here, then it will become eta, that will be cancelled. Eta will be cancelled. Eta square -1, that will be cancelled. That is fine. And on putting 1 I should get -1. I have to check that. If I substitute 1 here, I will get 1 plus eta and plus 1 minus eta, and ultimately that will be 2 in the numerator. And if I put 1 in the denominator, I will be getting eta minus 3, and on rationalization it will give, I don't think it will produce -1. Something is wrong. Oh, z minus 1, okay, z minus 1, 1 minus eta plus 1 and -1 minus z, that is fine. W plus 1 minus 0, and 0 minus 1 and 1 minus 0, that is also fine. Z minus 1, and I have, at this point I rationalized with the 1 plus eta. So 1 square minus eta square, that will produce 2, and 1 plus eta whole square will give 1 plus 2 eta, that is also fine. Minus was taken common, that is also fine. W plus 1 minus 1 cancelled out, and this will become W minus 1. Negative cancelled out, 2 cancelled out, eta into z minus 1, z plus 1. This is also fine. And here I applied component 1 dividendo. Okay, eta z, oh, this was eta, yeah. Here we had eta, right? And that's why I got an error in the answer. So it should be on applying this, where is that? Eta z minus, this is fine, and this is -1, okay, minus 1 plus eta. Now it is fine, right? Okay, so this is your transformation. And it is important to note that this transformation is not unique, because you can always multiply this with the same number. If you multiply the numerator and denominator by eta, right, then these coefficients will be changed. A, B, C and D will be changed. If you multiply it with 1 plus eta, again this will become, I think, 2, right, 2 eta, and this will become 2, and this will be also changed. It means that A, B, C and D are not unique, right, because one can always multiply the numerator and denominator by some constant, right? But the one thing is that this ratio is always constant. A upon C is always same in all cases, right? If you find this 1 plus eta over 1 eta minus 1, and you find its modulus, that is also always same in any case, right? Okay, so this is the required linear transformation, right? I will take another example. First thing is that we have to find the image of mod z less than 1. This is also remaining part. So in order to obtain the image of mod z less than 1, right, what I will do, I will put a test point belonging to this domain. Z equal to 0 is belonging to this domain, you can see that, right? And I will put z equal to 0 here. In order to obtain image of mod z less than 1, take test point z not equal to, let the test point be 0, and substitute that W 0, that will produce 1 plus eta and 1 minus eta. Sorry, this will be 0, 1 minus eta over minus 1 plus eta, right? And I should rationalize it, and I should rationalize it, right? And that will produce 1 minus eta, 1 minus eta. So it will become 1 minus eta whole square, and that will produce 1 plus, okay, that will be cancelled, minus of 2 eta, and this minus will be taken, so that will produce 2 eta, and in the denominator it will produce 2, I think, that will give eta, right? It indicates that this 0 point that belongs to this interior of this circle is mapped onto the upper half plane, right? This eta belongs to the upper half plane, right? So therefore mod z less than 1 is mapped onto upper half plane, because this point is belonging to the upper half plane, right? And that should be written as v greater than 0, right? Okay, now I will take another example. Example number 2, find the bilinear transformation that maps -1, 0 and 2 onto the point 0, 1 and infinity, right? Fine. So this time you have this point also, infinity, and when we talk about infinity, we talk about extended complex plane. Extended complex plane is the z plane adjoined together with that ideal point infinity, right? Okay, so solution, again using the same procedure. Here z1 is -1, z2 is 0 and z3 is 2, and similarly w1 is equal to 0, w2 equal to 1 and w3 equal to infinity, right? And then applying that cross ratio, and w minus w1, that is 0, w1 minus w2, that is 0 minus 1, w2 minus w3, and see that w3 is equal to infinity. So I will not write infinity actually here, I should write w3 here, and I will write limit w3 tends to infinity, right? And similarly w3 minus w, do not write infinity, right? Okay, equal to z minus z1, z1 minus z2, z2 minus z3, 0 minus 2, and z3 minus z. Okay, that's fine. And if you see this, because we have this limit w3 tends to infinity, so if you focus on this, you should take this w3 common, and also from the denominator you will get w over minus 1, and limit w3 tends to infinity, this will produce 1 over w3 minus 1, in the denominator 1 minus w over w3, right? And here I will have minus 2, this is minus 1, that will become 2, I think, and z plus 1 over 2 minus z, right? And you can see that if you approach w3 tends to infinity here, this will go to 0, this will also go to 0, and you will be left with minus 1, right? And from this minus 1 it will be cancelled out, so you will be having w equal to ultimately here 2z plus 2 over 2 minus z, right, is the required transformation, right? Or you should write it as wz. Okay, and you should always check this, if you plug 0 you should get 1, putting 0, yeah, I am getting 1, and putting z3 equal to 2 in the denominator, you can see that this is going to infinity, right? This transformation is correct. Taking another example, but I will change the scenario. In these two numericals, we are given the 3 points both on z plane and image plane, but this time I will provide the full image and domain picture, and we have to select 3 points, right? So that may be also the case when you are given the domain and the image, and you have to identify the 3 points correctly, right? In these numericals, 3 points were given and their images were also given, but sometimes you are not given the points, rather you are given the whole image and the whole domain, right? So third example is of that category. Example number 3. Okay, and this time find the bilinear transformation that maps this is Z plane, right? And this is W plane, right? And if I take a semicircle here, like this, right? And should I take the inside of this? Left, okay. If I take the outside region, okay, and if I take the lower half region, this is U axis, V axis, and this is W plane, this is Z plane, X axis, this is the Y axis, right? So shaded region is the domain, right, that maps this to this, right? And the shaded region is your domain, and this shaded region below this U axis is your range, right? In this case, you have to identify that bilinear transformation, but the 3 points are not given, right? You have to identify those 3 points and their images correctly in order to find that transformation, right? So the idea is that you just choose 3 distinct points. Let I take this point, and this point, right? And if I take this point is 1 and this point is eta, right? And this is a unit circle that is given. This is a unit circle, and this is -1. So we have 3 points, right? And similarly, we can also have 3 points here. This point is 0, and let me take this point as 1, and this point is -1, right? So, but remember one thing is that if I trace this circle, if I walk onto the boundary of this circle like this clockwise, then this shaded region will be on my left hand side. You just imagine that if you walk along the boundary of this semicircle clockwise, then the shaded region is on your left hand side, right? And similarly here, if you walk in this direction, negative direction of U axis, this way, then the shaded region will be on your left, and that's the key point here, right? You should take the order of the points Z1, Z2, Z3, and similarly W1, W2, W3, such that the shaded region is always on your left, right? Or it is always on your right. So I have taken that the shaded region should always be on my left, and that's why this should be Z1, Z2, Z3, because my direction of traversing is this way, clockwise, right? And in this case, the direction of traversing the U axis should be in the negative direction of U axis, so that the shaded region falls on your left, right? So take 3 points, Z1 equal to -1, Z2 equal to eta, and Z3 equal to 1, right? And similarly here, W1 equal to how much? This way, 1, W2 equal to 0, and W3 equal to -1, right? Okay. Now, using cross ratio, W minus W1, W1 minus W2, W2 minus W3, and W3 minus W equal to Z minus Z1, Z1 minus Z2, Z2 minus Z3, and Z3 minus Z, right? Now it all remains to simplify these ratios, and that will produce, I think, 1, 1, okay, W minus 1, and this will be W plus 1, and I should take minus common. Similarly here, I will have Z plus 1 and Z1 minus Z, okay, and on rationalizing it, I should take negative common. Negative will be balanced with this, that will produce 1 plus eta, and on rationalizing with the 1 minus eta, that will produce 2 in the denominator, I think, 2, and here I will have eta minus 1 multiplied by 1 plus eta. So ultimately negative will be taken common, 1 minus eta, 1 plus eta, so 1 minus eta, that will produce 2, right? I will check it again. here I got minus sign and that was cancelled with this minus, right? Then I rationalize with 1 plus iota, that produced 2 in the denominator. Yes, okay, and 1 plus iota multiplied by this thing produce minus 1 plus iota into 1 minus iota. I think this is not correct. 1 plus iota whole square, that will produce 2 iota, and 1 minus iota 1 plus iota, that will produce 2. Now it is correct, right? Okay, I should put this minus here, and now it will give w minus 1 over w plus 1 equal to, that will produce z plus 1 over z minus 1. This minus is absorbed here, 2 is cancelled, and iota, where should I put that iota? Iota here, iota, right? Now I will apply componendo or dividendo. On applying componendo and dividendo, apply C and D. I will get, if I add them, I will get 2w, and if I separate them, I will get 2. So ultimately this 2 will be cancelled, and on the right hand side I will get, if I plus z 1 plus iota plus 1 minus iota. The denominator, if I subtract, that will produce 1 minus iota z, and this will produce 1 plus iota, right? So this is your final required transformation, and you can check that if you plug iota here, that should produce 0. Iota cancelled, minus, yeah. So this is the final transformation, right? And you can also, yeah, that's fine, that is not required, only transformation what was required. So I will take last example. Example number 4. Find the bilinear transformation that satisfying w0 equal to 0, w1 equal to 1, and w infinity equal to infinity, right? So again you are given 3 points, but here if you input 0, you are getting 0, 1 is mapped to 1, and infinity is mapped to infinity, right? Again you are considering the extended complex plane, since we have infinity there, right? So I will start with the cross ratio. We have z1 equal to, z1 0, z2 equal to this much 1, and z3 equal to infinity. Similarly, w1 equal to 0, w2 equal to 1, and w3 equal to infinity, right? And using that cross ratio, w minus 0, 0 minus 1, 1 minus infinity, but do not write infinity, rather you should write w3, and here you should write limit w3 tends to infinity, right, over w3 minus w, right, equal to z minus 0, 0 minus 1, and 1 minus z3 over z3 minus z, and this limit z3 tends to infinity, right? So this time we have infinity on both sides, and simplifying it, I will get this will become w over minus 1, and on dividing it by w3, I think, yeah, that will produce w over minus 1, limit w3 tends to infinity, that will produce 1 over w3 minus 1 over 1 minus w over w3, right? And on the right hand side I will get z over minus 1, limit z3 tends to infinity, 1 over z3 minus 1, and 1 minus z over z3, right? So on approaching w3 tends to infinity and z3 tends to infinity, I will get minus 1 over 1 from here, so that will produce w over minus 1, and from here I will get minus 1 equal to z over minus 1, and from here I will get minus 1. So ultimately I will get wz equal to z, right? And this is called identity transformation, right? Identity map, right? Okay, so this is it for linear fractional transformation, right? In the last video and this video also, you learned how to find a linear transformation, right, with the help of only 3 distinct points given on the z plane and their corresponding images on the w plane. And in the last video, you learned how to find the image of some domain object with the help of this linear transformation, and especially a circle can be mapped to a line if a pole of the linear fractional transformation lies on the boundary of the circle, right? And again, a line can be mapped to a circle when the pole of the linear fractional transformation doesn't lie on the line, right? So these facts should be remembered in order to see the amazing things about this linear fractional transformation. This is it for this video. Thanks.